Hi Wildcats, this is Unit 3, Focus Question 1, where we want to look at electromagnetic waves, the energy that they possess, and how that can be applied to different applications. So let's start with talking about radiation, because a lot of times you hear it called EM radiation. Well, radiation is just the energy transferred by a wave or a particle. So in other words, electromagnetic radiation is just talking about the energy that radiates away from some source. So in this picture over here, you can see, actually let's start down here with the sun, right? This is radiation. Electromagnetic rays or waves in the form of light are leaving or radiating away from the sun, and so we say that those are that the sun gives off electromagnetic radiation. But really we're just saying it's just another way to say electromagnetic waves. And yep, they're caused by the vibration of atoms. So, what is radiation? Well, it comes in different ways, different types. Gamma rays, and then basically everything else. Gamma rays, radiation is everywhere. From the sun, there's cosmic radiation. Gamma rays, as we sit here right now, are traveling past us. It's given off by the sun, other cosmic bodies far, far off into space. It is given off by like uranium and radon in the soil, and that radon is released. So, if you've ever sold a house or bought a new house or in Bloomington or Normal, you know that we have radon in our soil, and that's why you have to have those big ugly white pipes put on your house to mitigate the radiation that might be coming into your house from the soil surrounds you. And that's naturally occurring. Plants have radioactive elements like potassium. Everyone knows bananas are good in potassium. Well, bananas are radioactive in the sense that they give off gamma rays in small amounts, background radiation. And then yes, even so like if you eat food, you are giving off small amounts of radiation because you possess slightly radioactive elements within you. And then finally man-made. Smoke detectors, nuclear power plants, I think that's obvious, but yeah, smoke detectors give off radiation, gamma rays. And then there's basically everything else. So radio waves, Wi-Fi, microwaves, visible light, UV, remote controls, those are all around us. And it's weird to think about, but if we could see across the electromagnetic spectrum instead of just visible light, we would literally be bombarded with rays and waves all over the place. So the question we want to address here is, how does electromagnetic radiation interact with matter? Well, sometimes it doesn't. We have talked before that the wavelength of different electromagnetic waves varies. So radio waves have wavelength the size of buildings or humans, right? 10 to the 4th meters, 10 to the 2nd meters. And then they get smaller from there, right? So when you get down to visible light, it's 10 to the -5th centimeters, and so now we are talking about single-celled organisms or molecules for ultraviolet. So those waves are very, very short, but sometimes they're big. So like radio waves have huge wavelengths, and that means they have a small chance to interact. So if this is a person and the radio wave is in size, that's its wavelength and its amplitude, then it's going to miss those people, and that means that they have a small chance to interact with atoms, which allows them to get indoors. If you're inside, you can still get radio signal usually. If you go underground or in your basement, it's harder because there's more atoms in between the radio waves outside and your receiver, but it's still possible. Visible light and ultraviolet waves have small wavelengths, which gives them a greater chance of interacting with atoms, and that's why a single sheet of paper or a t-shirt can block light, but yet radio waves can move in and around houses. They just flat out have longer wavelengths. So the question, how does EM radiation interact with matter? Well, sometimes it doesn't. Long wavelengths have a smaller chance of interacting with matter. Sometimes it does though. So smaller waves or smaller wavelengths will actually strike an electron of an atom. And so when we get down into these small wavelengths like ultraviolet, X-ray, and gamma rays, they're small and they have a good chance of interacting with atoms. So what do? Well, that depends on how much energy they have. Depending on the energy, small energy might just rotate the atom or vibrate it. This is sometimes what we associate with heat. And as you add more and more energy, sometimes it'll change the electron's energy level. We saw that before when we talked about photoelectric effect, and that, which is over here, and why radiation's given off, right? These electrons can actually jump from one electron level to the next and then fall back down, and that gives off electromagnetic waves. So that's caused by an electromagnetic wave coming in. It adds energy to the electron, which causes it to come up to a new level and then fall back down. And then finally, it can eject the electron as it has enough, if it has enough energy, which causes it to actually not just have the electron move up an energy level, but actually go firing off and leave the atom. So, leaving, I guess we should back up here for a second. When an electron, or excuse me, when an atom loses an electron, right? So here's a couple protons, and they are surrounded by electrons. 1, 2, and then we have one more out here, 3. If we get this electron to leave when it gets struck by a wave with enough energy, we'd actually have an ion, right? Definition of an ion from chemistry is a charged atom because it's missing or has extra electrons. So what this electromagnetic wave has done is it has caused an atom to become an ion. And so therefore we call this, we differentiate between them. We talk about ionization. Electromagnetic waves with enough energy, have the ability to ionize an atom, but not all do. So sometimes we have non-ionizing, where one type is non-ionizing radiation, and it doesn't have enough energy to actually eject the atom from an electron from an atom. And then there is ionizing radiation, which does have enough energy to do that. And so a number that you're going to want to know here is about 10 electron volts, and we'll talk about what that is in a second, is required to eject an electron from an atom. So in other words, if an electromagnetic wave has 10 electron volts or more of energy, it would be considered ionizing. And there actually is a line right on our electromagnetic spectrum where that happens. It's right here, and it falls right in the middle of ultraviolet. And so we are exposed to ultraviolet from the sun all the time. And there's different types. You might have heard of UVA, UVB, etc. So one type of UV is ionizing, / it will damage your cells and therefore cause you a sunburn, and another type is not. And everything above that has enough energy. So some types of ultraviolet, X-rays, gamma rays, all have enough energy to cause ionizing of atoms. And so that's why you don't want to get bombarded with X-rays for 24 hours a day, but it does us no harm to be surrounded by radio waves all the time. So, what is actually happening there? I briefly mentioned it a second ago. When we have enough energy coming in, it knocks an electron off of an atom. And while you're made up of lots and lots of atoms, some of them are involved in your DNA. And so if you actually have enough energy in that wave, and it penetrates far enough into your skin or cells that it goes through a DNA molecule, and now we are taking electrons and shooting them off of our DNA. Well, we are changing parts of our DNA in doing that, and what you end up having is what we refer to commonly is a mutation, right? So everyone should probably know at this point that getting sunburnt multiple times can increase your chances of getting cancer. Well, here's why. Physics is the answer why. Ultraviolet rays are ionizing, some of them. They have enough energy. You are bombarding your DNA with these ultraviolet rays. Some of them invariably end up interacting with your DNA, which causes electrons to fly off, which causes changes to your DNA. If you get a change in your DNA in the section that controls cell growth, you have uncontrolled cell growth / cancer, and you develop skin cancer or a skin tumor. So in short, the answer to biology of where cancer comes from or skin cancer comes from is physics. Okay, we talked about this. Higher energy waves can penetrate deeper. So UV, you don't have to, you could get burnt in the sun every day for your entire life and you're never going to get kidney cancer, right? Your kidneys are buried deep inside. Well, UV only has enough energy to penetrate your skin cells, the outermost layer. X-ray, on the other hand, can go all the way through your skin, but things like lead, which are really, really dense, will stop it. And then gamma rays, which have the highest energy, can actually go through your hand, through concrete, through many other things. So the more energy it has, the more dangerous it is in terms of its ability to move through matter. Okay, so we need to talk about that energy because we haven't discussed that yet. So how does the energy put in relate to the frequency of a wave on a spring? I know, why is he talking about springs? Well, if you remember, I stood in front of the class and I waved the spring, and we talked about if I move it faster and faster, I get a greater and greater frequency, or I have to put in more energy to make the frequency greater. Well, so the same thing is true here. As we increase in frequency, we increase in energy. You'll notice here is my ionizing line, right in the middle of, or excuse me, not there, right in the middle of ultraviolet. And so these have the highest frequency. Ultraviolet, X-ray, gamma rays have the higher frequency, and therefore they have more energy. And so it turns out there's an equation that can allow us to calculate that. The energy an electromagnetic wave has is equal to a constant called Planck's constant, which is 6.63 times 10 to the negative 34th joules times seconds. And this is going to be a number, it's given to you on your equation sheet and on any assessment, but you're going to need to be able to use this number. Times frequency. So if I want to know the energy that an electromagnetic wave has, I take its frequency, multiply it by Planck's constant, and then that number will give me my energy. It will give me my energy. If we think about this for a second, we're going to be left with multiplying these numbers. Energy will be equal to the unit of Planck's constant is joules times seconds, and I'm multiplying that by frequency, which is hertz, or in other words, 1 over seconds. So my seconds will cancel. I'll be left with energy in joules, which is a unit you're familiar with in chemistry, but in our terms it's more convenient to talk about things in electron volts. So 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So this will also be something that you're given, but it is a new conversion factor that we'll need to be able to use. So let's see if we can do a problem. It says, how much energy will a photon with a frequency of 5.25 times 10 to the 14th hertz have? And then give our answers in electron volts. So the equation is pretty straightforward. E is equal to Planck's constant times frequency. So Planck's constant is, if we don't remember, we didn't write it down, 6.63 times 10 to the negative 34th. So 6.63 times 10 to the negative 34th joules times seconds. And then the frequency they tell us is 5.25 times 10 to the 14th hertz, or 1 over seconds. Cancels. The energy that this photon has is, I need to put that into my calculator, 6.63 E negative 34, close parentheses, 5.25 E 14, and I end up with 3.48 times 10 to the negative 19th joules. Well, we want this in electron volts, it says. And so I need to convert this joules. I know the conversion factor, or they told me. If you don't remember, it's on the last slide. 1 electron volt is 1.6 times 10 to the negative 19th. So 1.6 times 10 to the negative 19th joules is 1 electron volt. So cancel those. And I can just take my answer and divide it by 1.6 times 10 to the negative 19th. And my answer, this photon has 2.12 electron volts of energy. So the final question is, if this struck an atom, would it result in ionization? And then so we need to go back and look at our notes, and it said ionization occurs at approximately, because it varies, 10 electron volts. So since this photon has less than 10 electron volts of energy, I can say that this is non-ionizing. So this electromagnetic wave would not have enough energy to actually damage the DNA of a cell. So I hope this helped in terms of understanding how to calculate and what is the ionization energy of an electromagnetic wave, or excuse me, how much energy an electromagnetic wave has, and whether or not it is ionizing. As always, please use the resources that you have on Google Classroom if you have any additional questions on this.